What is the hydrophobic interactions? How important is it? Where does it manifest itself? These are three important questions that we tackle first using examples. We all know that cells in our body exhibit a most important interface, a phospholipid bilayer membrane that allows some chemicals to migrate into the cell and others out of the cell, that allows the transport of electrical charges and even enable the cell to deform mechanically. This membrane is constituted by amphiphilic molecules, that is, by molecules with both hydrophilic and lipophilic moieties. Such molecules, as we shall see, prefer to self-organize into structures that present their hydrophilic side to water and their lipophilic ends away from water. The same situation is encountered in liposomes and micelles and in proteins. These structures owe their existence to the fact that water molecules and non-polar molecules do not like each other and will not dissolve significantly into each other. The famous oil and water illustration. The intermolecular forces at play between amphiphilic molecules and between amphiphilic molecules and water explain why water beads on the lipophilic surface of a leaf, and why milk exists as a dispersion of droplets of fat and micelles of proteins in a mostly aqueous suspension. To start our discussion of the hydrophobic interactions, let us examine what would happen if a lipophilic molecule, such as hexane, tried to dissolve into water. On this cartoon, we represent the methylene and methyl groups of hexane by black beads, and the water molecules by blue or white beads. Upon dissolution, the hexane molecule would displace the free water molecules, the white beads, and become surrounded by cage water molecules, represented as light blue beads, which form what we call the solvation shell around hexane. Cage and free water molecules have vastly different properties. First, cage molecules exhibit less favorable interactions with their neighbors than the free water molecules, since hexane is nonpolar and cannot form any hydrogen bond with water. So, the cage molecules will have a higher enthalpy than the free water molecules. Cage water molecules also exhibit much lower entropy than the free water molecules, since their translational and rotational motion are hindered by the presence of the hexane neighbor. So, in summary, the dissolution process of an alkane into water can be viewed as resulting in the replacement of free water molecules that have higher entropy and lower enthalpy, that is, lower Gibbs energy G, by cage water molecules that have lower entropy and higher enthalpy, that is, higher Gibbs energy G. Hence, such a process would lead to an increase in G, that is, delta G positive, and cannot occur spontaneously at constant pressure and temperature. So, how did nature manage to manufacture the membranes that cells need to build their walls and protect their inner components? What kind of molecules can interact sufficiently with water to be partially soluble in water, but yet would aggregate to form solid-like structures when their concentration becomes sufficiently large? These molecules are amphiphilic molecules, molecules with both hydrophobic and hydrophilic moieties. Let us compare what we have just discussed with what happens when amphiphilic molecules are dissolved in water.